Okay, seems to work. Good evening, and just hope everything is good, including the sound. How to say, if anybody wants to give me feedback on that, because I pushed the mic a little bit. I was asked to, so if you can tell me anything, thanks in advance. Anyway, in the meantime, today we're going to keep working on our virtual machine, and let me remind you a bit what it is about. So we have a huge list of value on which we are going to apply some predefined functions. And as these slices are big, we want to run the function on each element in as a parallel fashion than we can. And so if you were to write them, it would be a simple for each on each element, and then you apply the same function over and over again. But in our case, we are going to we are taking slices of the big slices, applying in parallel fashion the function we want to compute, and storing this chunk of values back to the big slice, taking the next chunk and starting all over again. And what we want is we want them to be as fast as possible. So we're writing them in assembly. And as we don't want to write all of these functions because there are like half a dozen to 10 of them, we don't want to write each of them on each architecture that we want to support. Tract supports Intel, which comes in basically two flavors. One flavor is AVX2, the other flavor is AVX512. We support ARM7 with the SIMD extension, which is called Neon, and we support ARM8 with its own version of SIMD, which is called Advanced SIMD, but many people will refer to it as Neon as well. So in order not to do a big matrix with all our activation function in a row and all our architecture in a column and have to write assembly for each of the cells, we are doing some bit of virtual machine. So basically we are describing all of our function in some kind of microcode or some kind of bytecode. And we are implementing an interpreter for this bytecode in each and every platform. For now, we are only focusing on the ARM8 platform with Advanced SIMD. Excuse me. And where were we last time? So this is an int session on this little project. We have covered a lot of ground, but last time we kind of hit not a snag, but it was starting to be complicated and the session was already pretty long. So these are the functions. The one I call block-1, so the first set of functions that we want to evaluate. Then we have others which are coming later. This is more or less the microcode that we are using for these functions. And last time we got stuck with some kind of difficult to observe simple operator. So let me try to clarify this or refresh your memory if you were there last week. So our microcode is defined in SRC frame. So in this linear crate, which contains all of the low-level compute functions of Tract, we have the frame module, which contains all of the non-architecture dependent code in this. So basically every single optimized operation contains something in frame that in turn will call more stuff which is code in assembly for each and every platform. So frame is where all the generic code goes. And as a matter of fact, we also have a generic called folder, which contains a fallback implementation in Rust of the low-level kernel, so that if we go to a platform where one or the other of the kernel, the low-level kernel, is not implemented, we at least have the Rust fallback to be able to run neural networks. So our topic is activations. And if we look at the top level module, yes, we can see here our, or maybe rather this one, we can see here what our assembly looks like. And so the idea is our interpreter fetches a list of these, a sequence of these. It will iterate over them until it finds a down operator, which is coded as a 0. And then all of these are the individual functions that we need to run. For the block-1 activation functions, only these are required, and maybe not all of them. This one are for more complicated stuff like sigmoid and Tanch, for which we already have assembly implementation, so there is no real rush. So we've struggled a bit with this. Like, I think it was 2 sessions ago, to find the right way to encode these operators, and we have. The key is the discriminant of the enumeration is coded on 2 bytes. So this takes 32 bits, so 4 bytes, but the first 2 bytes will contain 0 for down, 1 for move, 2 for load, etc., etc. And then for these 2, move and load, we have 1 more byte that contains the register IDs. For this function, we take a constant. It's a trick that we implemented in, I think, the same session. It was 2 weeks ago, or maybe 3 weeks ago. Actually, I start to get confusing now. Where we put the actual constant as the next operator in the flow. So our flow of instruction either contain one of these or a constant that follows one of these 5 operators. Anyway, let's have a look at these, because last week we tried to implement a move and load, because one of the difficulty is it's a bit difficult to observe just one move or one load. The reason why it is difficult is our virtual machine will preload one of the 3 registers. So we have 3 registers called A, B, and C. So the virtual machine will put the input value in A. And then we have some function like frame activation definition. So we are trying to do like, yes, maybe this one. I don't remember which one we are working on, but it doesn't matter. So in this one, we are trying to implement a move from B to A. So we are, no, sorry, a move from A to B. It's always go, the first register is the destination and the second is the source. But in order to observe this with a simple test case, I need to load something in B, move it to A, and let the framework write the result in A. Because that's the key, actually. The framework will load the input value in A, it will run the various operations, and then it will store the value that it finds in A, in place of the values that it found as input. I hope I'm not too confusing here. But it didn't work, and I don't know why. And we're at a point where, it's nice when we can devise tests that only test one operation, but in the case of load and move, we need to test both of them together because we can only observe what happened in A and we can only change what happened in A if we don't use load. So we need, so we have a choice between extending the language so that we can observe B or observe C, but I don't like it very much. I don't want to make it more complicated than it is already. So I think we're going to debug, and okay, that's how it is. We cannot write unit tests for load and move on their own. We need to have maybe two of them to be able to do something. So let me find where these tests were. So we managed to run a couple of them. So for instance, in this test, we're loading a constant to A, and if I remember correctly, this one works. And this one is observable because the framework will put something in A, then we will execute this function that will load something that we define, which is a const over there, into the A register, and then the framework will store this value back in memory, so we can observe them. So let me try to remember how we run the test for this thing. Test and load A prop, or let's do load. A bit of compilation here. What's wrong with this? What did I do wrong? Cargo dinghy Wendy recipe. Yes, I'm not in the right place. Now I am. Compiling. Pom. Maybe I should go and grab my Switch and play Zelda instead. I don't know. Okay, so now it's done compiling. It's moving bytes around. And I think these machines are connected by Wi-Fi, not by Ethernet. Yes. Okay, so load A is working, load B is working, load C is working. So we are running our test on each and every implementation of the kernel that we have. So this is the Rust fallback implementation, and this is the ARM64 SIMD implementation. So the three of these are working. So this one, and that one. And the next step. The next step is to try to get these also to work. So I remember that it didn't last week, but I don't remember which one was failing. Move B to A. Okay, so that's the one. So what does it do? Move B to A will load a constant into the B register, and then it will move B to A. So we should observe the constant, which is exactly what this test does. The test say that whatever the input value, we should observe the constant. Okay, so this test is failing. That's good. We know where to start. And also, what we have here is a lot of stuff, but I think we also made a simple. Nope, not yet. Okay, so we'll do it. We'll do this. What we are doing here is we are doing some property testing, and the good thing with property testing is that it reduces the error to a minimal test case. And I'm starting to wonder if it's really minimal, because the constant looks wrong to me. It should be more minimal. Like it should be 1 or something, or -1 or something like that. But I can see usually when there is something is wrong here. Sorry, my screen is off. Is it better now? Yes, okay. Sorry for that. So we have a minimum failing input here that we can use. I'm just surprised that the constant could not be made simpler. Because the rule to generate the constant, if we look at our test, which is move B to A, move B to A, the constant is generated by any ti, and ti is a float, so I think that it should reduce in a more nice way. It's not too bad. From this we can actually try to make a simple test. So let's do that. So this is a prop test that picks random values to run different tests and try to find new cases that are failing. But what I like to do is from these from this prop test, I derive unit tests. So in that case, we have the minimum input here. So it's it has to be. We have a few -0 here. So that's very. I don't think it's been reduced correctly. That's a bit unpleasant. And the fact that we have a stack trace doesn't help, but I think it's related to stack trace come from Dinky, which put them by default, and I'm not sure how to not have the stack trace. So, well, that's okay. We manage. So hopefully I will manage to reproduce the problem easily. So now I'm moving from a prop test to a regular test. So I'm going to use x of 0, and how many 0 do I want? I want char nr zeros, because I can only call the kernel with a multiple of nr values. So this can go away. Up. And so, okay, still not good. Cannot call non-const in constant. Okay, that's not too bad. We'll do it in 2 steps. Or maybe I can do this actually. Yes. This and that. Okay, no. Yes, it has to be. It has to be a 0 for ti. So this is going to be ti. I mean, it could be anything. Just that 0 is the easiest value to get in this very generic test. And then the const will take 1. And we'll try this. I think it should work, because all the instances of ti can be casted from f32. So we should be fine with this. So let's see if this reproduces. I see an old friend joining. Murdix, welcome back. Welcome. It's been a long time. Compiling, installing. I actually have a bit of room over there on my screen. I can save this. Yeah, let's save some real estate because we're going to need it if we do assembly debugging. Up. Here we go. So our test fails. Okay, so we have a single test that we can run now. And why is it failing? Because we should see ones and we see zeros. So this is just not working. Okay. Next step is actually debugging. And okay, so that was my Raspberry Pi. I did update just right before joining. And let's say it does need to reboot. Nope. Okay, so that's fine. And so if we go to wherever Dingy put its test files, we should see. So how was it called? It's track linalg dead. Easy. So Dingy tracked linalg dead, and we need to run it with the test filter, and the test filter is move b to a0. And I will use actually the full name of the test because there is also the generic test which has the same name. Okay, it's still failing. That's good. Now, do I have GDB? Yes, I have GDB. And with GDB, I'm calling first the executable. Reading symbols. I think it has symbols, and I'm going to put a breakpoint in the assembly activation function, which is called, let's see if it finds them. So ARM64 SIMD. Nope, that's wrong. So nope. Okay, so let's try and find out what is the name of the function that we are calling. So it's in ARM64 SIMD, ARM64 SIMD activation F32. So the function is ARM64 SIMD act F32 blah blah. So ARM64 SIMD. It doesn't look like it finds it, which, yes, okay, here we go. Make breakpoint depending on future. Not sure it does work, because usually it finds them right away. Yep, no breakpoint. So last time we hit that one, it was because I was using a release build, and this time I'm not using a release build, but maybe I'm stripping the binary. Let me check. Raspberry 4. Here we go. That's not this one, it's this guy, and I'm not stripping. So what's wrong here? Let's try to find, because there is this suffix and everything, so let's try to find the real name of the function. So we know it starts with ARM64 SIMD act, and the intermediate assembly file is somewhere over there. SIMD, not SIMT. Okay, so that's the name of the function where I want to break. I think. Let's try again. Break. Much better. We have a breakpoint. Let's run. And we Hit breakpoint 2, so it cannot show the code, but that's fine. Okay, so we have a break. So let's switch to ASM. Here we go. So maybe I need to remind you of the assembly code structure. It's a bit convoluted. SIMD act. Okay, so this is just preserving the register that we need to preserve. That's dictated by the calling convention on ARM64. But once we are there, so this is not super relevant, but in X2 we get the len of x's. So this is the number of values that we must process. In X1 we have the pointer to the first of these values, and in X0 we have the pointer to the first operation that we must process in the loop over each element, over every element. And we have two loops. So the outer loop is a loop that goes over the chunks of our slice, which starts at X1 and is X2 long. And the inner loop is the loop that goes over each and every single operation in the little program that computes the right function. So the inner loop use a jump table to jump to the right element, to the right operator. So we have done when we are done, and we have the move. The operator number 0 is done, number 1 is move, and so if we find a move, this bit of code will jump us to this place where we actually have a second jump table where we look at the various combination of A and B and C. And the interesting thing is, as we have 3 registers, we only have 6 valid moves. We have 6 valid moves, and so moving A to B, A to C, B to A or C, moving C to B or A. And we also have 3 moves that are no-ops, so moving A to A, moving B to B, and moving C to C do not do anything. And so what I did try to do is I tried to shift the ID of the destination registry and the source registry into one single byte, and then write a jump table that work on the first value possible. And actually I'm just using half of the byte, so the lower the 2 bits, the 2 how is it called? The 2 bits of the less values are going to match, are going to contain the destination. So here is how it works. In W6 I have the full opcode with the actual opcode and the 2 registers. I'm shifting to the right by 16. Oh, this is already wrong. Yeah, this is already wrong, because here I'm shifting away. Is it right? Let me see what I'm doing to decode the main operator. So no, that was correct. Is it correct? Okay, we're going to debug and see what it does look like, because we are a bit lost here. So let's see. So we are entering our function. We are doing some zero length checks, doing the outer loop bit. So we are loading some values into our registers and computing some addresses. And this is where I start. So we are going to load two operators from the operator stream. The first one in W6 and the second in W3. So if I look at W6, sorry, what? This is not expected, yes, because syntax is, try again. All right, so 65538 and this value what I'm going to use, I don't want to use Python, I don't like Python. So we need to look at, not sure what this is, okay. So we have a value of, and I want to see them in bytes, 65 what? 65538. All right, so what is it? Here we go. So we have, so this is 32 bits. So this is 4, this is 4 more. So this is 1 byte. So then we have 1, 2, 3, 4, 5, 6, 7, 8. And this is another byte. So we have 1 byte full of zeros. 1 byte that is 2, which I'm a bit surprised. And this is the one from the 16 leftmost bits, which contains the opcode. So that is correct. The opcode is 1. But now I think we are going to, yes, we're still in the inner loop. So in the inner loop, we are going to no, I'm wrong. I'm confused. I am confused, and I am confusing as a consequence. So the layout. What the assembly tells us, and that part is working because it's working with other elements, is that basically the 2 bytes to the right of our value, which this line will fetch, will isolate. So these 2 bytes have to be the opcode. So the opcode is 10, which is 2. And it's a good thing because down is 0, move is 1, and load is 2, and we are on load. So this is where we are going. And okay, so let's check it. Oops, double N. So we are computing the address, and we should jump to load. Bingo. And so we'll jump to load. And now we are trying to decode the rest of our bit sequence. So we have used this part of the bit sequence because it was coding a 10, which is a 2, which is a code for move. And now we need to figure out the rest. So this is irrelevant for now. And so basically here we are loading the constant that we are going to, we are loading one instance of the constant into our V24 register. Which constant did I pick? I think I pick a 1, and we will check that in v24 we have some ones. So the debugger doesn't know how to interpret the value, so it shows everything. And so we loaded in the first lane of v24 f32 worth 1, so that's this one. Okay, all right. And now we are trying to compute in which register we need to load this one value. So first thing, we are shifting 16-bit our integer to the right. So this will cancel the opcode that we already used. So now if we look at W7, we should just see a 1. Bingo. And this line will just cancel out bits that could be in the other byte, in the first byte, the one which isn't used in our integer, just to avoid case where, it shouldn't contain anything, but better be sure. Because nothing prevents the compiler to put any kind of crap over there. It's a load. And so now we are again on a jump table. It's a lot of jump table for load, and so we are computing an address, and as the value was 1, we should fall onto load B. Let's see what happens. Load B, good. We're going to load B. So the B register is made of the SIMD register 8 to 15. This 0 to 7, all of these are the A register, and these guys are the C register. And so we are dumping the value from V24S line, the first line of V24, where we check that we had a 1. So in V8 to V15, we should have all ones. Let's try. Okay, and let's pick 1 in the middle. And it's P $V 13.4S. What? Yes, it's just PV13. And yes, so single precision floats, and we have our for 1. So the load seems fine. So we are back at the top of the inner loop, and we are going to decode the next element, which should be the move from B to A. So let's see. So this is the opcode decoding and jumping. So we should go to move. Yes. And so now we are moving to the third and last, hopefully, jump table. And so first things first, we do the same of erasing these right 2 bytes in the value. So let's see, I'm going to check W7. It should be what? It should be 1. It's not. Yes, no, because we are moving B, which is 1, to A, which is 0. And the lower, the lower byte should be destination, so A, and it should be 0. And the higher one should be the source, which is B, so it should be 1. And that's right. We have, this is 1 followed by 8 zeros. So now we are going to isolate from W7 we are going to isolate the last byte, so we should see a 0. Correct. What else? We are making sure. Oh yes, so now we are extracting from W6. We are extracting the other byte. So it should be. So it should be 1. And it is 1. And now we are going to, yes, so this line is still to make sure that we're not grabbing extra bits. And here we are taking W7. So W7 was the destination. And we are going to add to W7 W6 shifted twice to the left. So the result should be 4 because W7 is 0 and this is shifted twice to the left will be 4. Let's check. 4, okay. And 4 should be move B to A. So 0, 1, 2, 3, 0, 1, 2, 3, 4. Yeah, okay. So we should jump to move B to move B. Huh. Yes. I think I wrote the jump table. I mean, I think that's where the problem is because we should go to move A from B. I mean, I'm switching between I'm switching the order of the two registers all the time, I guess. So here, okay, we will need to clarify that. We will check what happens, but so which one will we pick? We're picking move. Okay, so we're moving A to B. If I'm sticking to the convention, so this code decodes the other way around. So here we should just switch W6 and W7 actually, if that's correct. So let's see what move B A does. And so the destination is B. Okay, that's it. The destination is B and the source is A. Notice that to do a move, we need to do an AND of twice the same register to put it in the first register. There is no equivalent move in these SIMD registers, but it's fine because this just takes one cycle. So as far as I know, it's the fastest way to do the move. Okay, so what we did wrong is I got confused here between the registers. So if W7 is dest and W6 is source, then the one I should shift to the left is W7 and not W6. So I'm going to change everything to so I can keep this one. So I'm shifting yeah, so this comment was wrong, but now it should be fine. And then the rest should be correct. Let's see. Compiling, installing. Boom, 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 boom. And the test is passing. Okay, that's good news. That's very good news. So, it was a minor error, but at a crucial place. So yeah, the fix is this. We switched W6 and W7 in there. Very small one. Okay, let's see if we have more failing tests or if everything is happy. I haven't seen any red. Oh, there is red. So hard-sigmoid and hard-switch are failing, and we are failing kernel function return non-zero run. Okay, so non-zero run, the kernel function returns 1 when it hits an unimplemented sub-operator. So if we look at hard-sigmoid, we will see that it uses one of these operators that we haven't implemented yet. Let's check frame, definitions, activations, definition. So definition contains the high-level functions in terms of the low-level operator. So we are at hard-sigmoid. We've done these two. Really? Let's just run this one because I'm suspecting that these are error for nodes. They are sigmoid. Okay, let's try it again anyway. Compiling again. Yeah. Wrong machine. Okay, so failing, and it fails because it fails kernel function return non-zero. So mul const, add const, min const, and max const. I thought that we had all of these, but nope. So we're going to check. So ARM64 activation, SIMD activation. It's mouthful. So these are the moves, these are the loads, and add const. Min const isn't done yet. Okay, let's do min const. Shouldn't be too hard. Jump is wrong. Okay, and instead of max, it's just a min. It was okay. Min. Here we go. I think this should give us hard-sigmoid, and what I'm going to do right away, and I should have done that before actually, is max. I'm going to add a test for min, a unit test, load B. So these are loads, listen, okay, that's max. And after max, I'm going to add min. Okay, hard-sigmoid is working. I'm still adding the test for next time, because these tests we are using them today for the ARM64 coding, but one of these days we will be starting to code the ARM7 or the Intel kernels, and all these tests will come in handy and they will work. I mean, the test route will work right away. So it's worth taking the time. So we have one remaining, which is hard switch, if I remember correctly. And we'll also do the subconst, even if it's not used by any operator, but more for completeness, I guess. Let's just test the full thing once. Oops, error. So that's our switch. Okay. So we've done our sigmoid. Right. Git commit. Our sigmoid. Okay. And now the art switch. So the art switch complains about one function not being implemented. And if we look at the definition of art switch, which is here, so there is a bunch of crap to compute the constants. Move. Okay, so we've done this one. Mul const, add const, we have them. Min and max, we have them. But we don't have this one yet. So what this one does is it will do a times equal b. So basically compute a and b and save the result in a. So let's try to implement this. ARM64 SIMD, ARM64 SIMD act. And we are going to put it, so that's mul here. So that one is pretty easy. I think it's fmul. And we are going to multiply. We have some examples here, actually, yes. So destination is v0.4s, and we are using v0.4s, and we are using b. So b comes from v0.8s. And changing these by back to inner loop. 1, 2, 3, 4, 5, 6, 7, 8. Here we go. Now this is a situation where my key bindings and VI are really not being nice with me. And so this should be, so I already have that somewhere. Yes, so we're going to reuse A's like that, space maybe. And we need B's. And B's, I have them here. These are the B's. Donc, past. Okay. And let's see. And the test. The test, the unit test for mul. The unit test for mul. So we have mul const and we are going to add mul. Mulprop. So how is this going to work? We have x and we need b's. And b's are a vector also. And so we are going to load. We are going to load in B. We are going to load this value which is called V, and then we are multiplying it with B. And now I have a problem because my function here doesn't work. I need to know the index of x to be able to grab. I need to do x times v of ix, where ix is this. So I will need to change all of these to add the index. Not great, but okay, let's do this. So I'm replacing x by this. Okay. There are a couple more over there. This one should work, and I need to change the definition of this function. Oh, I have more over there. So instead of taking ti, it will take index, so use size ti, and call and return ti. And so here I will need to enumerate to get the indexes, and then it should work. And next, yeah, probably a bit more to fix. So what's wrong here? Oh, oh no! No. Okay, forget about it. We're not loading a vector, we're loading a constant. I'm thinking ahead. I'm thinking ahead like 1 year from now, because when we're done with activation function, there are other functions that we can do. Okay, so back to business. V is not a vector. V will be any ti. Okay, and now we can do x times v. And that should be better. So let's test if mulprop works. Okay, our tests are good. Maybe I will just take the opportunity to show what happens with, I mean, how prop test is incredibly helpful. For instance, let's say that there is something stupid in there, like something like that. Up, if I do this, I'm not testing the right one. I changed mul const and I'm testing mul. So we'll have to try again. I'm letting it go because I can rerun the test without changing it, so it should be fast. Okay, that one we can kill. And so if I'm doing mul const prop, so here what we have is we have the minimum failing input, and so we have some weird value from alpha. I'm not too sure why you get so ugly values, but the good thing is we know that it fails when this value is affected. I mean, we know that the failure affects specifically this value. So from there we can say 1, 2, 3, 4. So that's the last line, and 1, 2, 3, 4. So that's the one before last. and from there you can just try to figure out, and oh, okay, this is the one before last, this is where I got wrong. So prop test is super helpful in this kind of situation, because it saves a lot of time setting up tests and going to the debugger. So it's really a great tool to be able to use. So these 5 guys are the one we need for the other activation function, I think. Let's have a look. So, leaky relu needs if pause, and threshold relu needs if pause too. Okay, so we still have, we probably still want to do if pause and else. We have absolute, recip, add subs. We have subcons that we haven't done yet. Okay, we still have a lot of ground to cover, even with the simple ones. So let's see where we are with our tests. So we have relu, affine, hard sigmoid, hard switch. Let's try and do leaky. So leaky was after affine, and the definition is there. Oh, so it's one with the if x positive. Okay, so I'm going to copy this. Okay, and it was after affine in our initial assessment, so let's skip the right order. So this is going to be leaky relu prop. And yep, this is where it goes. So we don't have a beta in this test, we only have x and an alpha. And we are going to use the standard, it does nothing standard at all. We are going to use relu with alpha as a definition of operators. And this, so here I need to check against T0. So it's not called T, but it's called TI, because we are in a macro, which is always pleasant. Cannot find relu prop, oh yes, because it's not relu prop, it's leaky relu. And so this test should fail with the returns, kernel function returns 1 instead of 0 or something like that, which signals that we are missing one specific operators, at least. I'm trying to adjust a bit the light, and it goes by a huge jump. It doesn't show too much on the camera, but here it's very low, and it's really blinding, so I need to do something about that at a different time. Okay, so yes, I just asked for the wrong test. So we want to run leaky, and it's failing, and it's a good thing, and it's because kernel function return on 0. Okay, so leaky needs if then else. So we're doing the prop test for if then else. If then else, And so if then else only needs a vector of inputs, except how are we going to do? We will need to put something in B and something in C, so we can actually check that what we are doing is valid. So I'm going to put ones in, I'm going to do it like that, 2 in B's. I'm going to put 3s in C. Then I'm going to do if then else. Completion is not helping me a lot here. So it's if pause then else, yes. What? Come on. If pause. Okay, don't remember what I used. That was like 10 sessions ago. So if pause TE, okay. So I'm trying to make it a bit more consistent. If pause TE. Okay, and the result should be X if X positive. So positive or strictly positive? It says positive. So positive. So if X positive, then we're going to take 2 as TI, else we're going to use 3. And the formatter doesn't work because I'm in a macro, so I'm going to format it by hand. Load 2 in B, load 3s in C, if pause then else, and my test reference. So I'm closing these, and I need that. Oh, there is one too many braces here, and so this I will use 0. Okay, so we have our simple test, our unit test. Let's see if the test is failing as we expect. And it should be, there is no reason. And we're going to look into how to implement that, because it's not trivial actually, if I remember correctly. So where are we? If positive then else. Okay, so that's the one we want. And so we need to compare. Floats to zeros, and then we need to select one of the values from B or from C depending on the result. And I'm actually yes, okay, opening again my huge PDF with everything about ARM64 and trying to remember what we can use to do this, because we need to do it in vector fashion. We will not compare every single value. I'm not sure we could actually do it like that anyway. So this is conversion, this is bit clear and exclusive or perform a bitwise and no, that's not it. What is this? Okay, yes, no, not at all. I think this is interesting. Read each vector element from the destination SIMD and floating point perform bitwise and no. and the complement of an immediate constant and write the vector to the destination SIMD and FP register. What? Alors, bitwise, bit clear. Let me try to guess. I think this one is the right one. This instruction set each bit in the destination SIMD and FP register to the corresponding bit from the first source SIMD and FP register when the original destination bit was 1. Otherwise from the second source SIMD and FP register. Okay, so that's half of the story. This is so let's assume that so this apply a bit mask. So it will go over every bit of a vector, and if the value is 0, then it will pick the value from the second operand, and if it's 0 from the third one, or the other way around, it doesn't matter. So that's half of the story. If we manage to have a bit mask, so where all the positive floats are given 1 and all the negative are given 0, then this will do the rest. And I realize that I need to be mindful. Yes, okay. So that's part of the story. And then we have compare sign integer. So no, not integer. We are working on floats. So let's see. FACV, floating point absolute, compare greater than or equal. This instruction compare the absolute value. Nope. Let's see. We have this floating point conditional signaling compare scalar. This instruction compare to SIMD. Nope, that's not what I want. I mean, this will put flags, which is not what I'm really interested in. Floating point conditional quiet compare. This instruction compare the two SIMD registers values and write the result to P state. No, I don't need P state. Compare equal. This instruction compare each floating point value from the first source with the corresponding floating point from the second source, and if the comparison is equal, set every bit of the corresponding vector in the destination. We are getting closer, because this will make a bit mask with all 0 and all 1s for each value, depending on the observation on operand 2 and 3. We need the same one, but with not equal, but greater or equal. And I guess this will be nice. And we also have this one, which I think compared to 0. So this guy takes, compare this guy with this one, and for each lane we'll put 0 or 1s in here depending on the result. And this one doesn't even need a second operand because it will compare to 0. So this one looks pretty good to me. Let's check. Floating point compare greater than or equal to 0 on a vector. This instruction reads every floating point value in the source register, and if the value is, so the source is hn, and if the value is greater or equal to 0, sets every bit in the corresponding vector elements in the destination SIMD and destination register to 1. Destination is HD. Whoa. And otherwise set every bit of the corresponding vector elements in destination to 0. Okay, so this is our bit mask. And the BSL is our selection. All right. So that's the one. FCMGE. Okay. Let's try this. So FCMGE, and I'm applying it to So I'm comparing values in the first, in the A register to 0. I'm just strictly mimicking the syntax over there. And so I'm comparing V0 to 0, and for each of the 4 lanes, I'm writing zeros or 1 into itself, into the same place. So I'm destructing the previous value, but that's what the instruction is supposed to do. 1, 2, 3, 4, and 1, 2, 3, 4 again, and these are our A's, and I can discard these. Here we go. Let's try to fix alignment a bit. Yes, nice. Okay, so that's the first part. At this stage, we have the bit mask. Now we need to apply the bit mask, and so the bit selection function is BSL, and BSL. So this function, the first function works on float. So it has the f prefix and it does arithmetic on float, but this one only works on bits actually. So we can use any of these. We're going to use this arrangement, which is it should be 128 small b. Because it will operate on each and every of the single bits of the vector, but it's actually, that's the one they're using in the syntax. If we use this one, we'll only process the first half of the vector. So that's the one we want to use, and BSL. And so the question is, what is the right order for B and C's? So the comparison will put, if I remember correctly, the comparison will put once if the first, not the right one, compare, it's F, the same with an F, CMGE. So this is the one that we used, and if the value is greater than equal to 0, set every bit of the corresponding vector element to 1, so positive 1. And for us, positive is B. So we need BSL, corresponding bit from the first source when the original destination bit was 1, or the right from the second. So it's B and C. It's in the right order. We don't need to swap them. So B for S, common fingers, and C, C's are at V16.4S. 1, 2, 3, 4. 1, 2, 3, 4. And I'm going to, I'm not sure why I did that actually. So let's put the A's. Then the B's. So these are the B's. And they come with space, which is good because it makes editing easier. And our C's, where are you? Load C. Here you go. These are the C's, and I don't need the comma this time. Up, missed it. If pause, yes. Bit of space. Okay. So let's try it. Fail. Okay, so yeah. So the arrangement, I talk a little bit about it. So we for BSL we don't look at the vector as vector of 4 floats, but instead as a vector of 16 bytes, and it's, as I was saying before, it's a bit arbitrary because what did I do? Because any arrangement would work actually. Doesn't work. So we have 3 where we wanted a 2. Okay. And it's at the first position, and so it's for D0. Yes. So here I'm comparing to 0, so greater or equal. And I think that in the code I may have put a strict superior, strictly comparison. Let's have a look. Frame activation tests. So it might be as simple as that. Where is it? Where are you hiding? If post, yes, that's it. Plus there is this weird thing with a float. Float has 2 zero values, a positive and a negative value. So I just hope this is not going to bite us now. I don't think so. Well, I guess this one returns as a positive 0. I'm not worrying too much about using strictly positive or just positive, because most of this time these functions are meant to be continuous, so it shouldn't matter. Okay, and now it's working. So the question is the out switch working now? Switch. It does work. Wunderbar. Okay. So we have added mul, we have added if post then else, and we made some formatting edits, plus lots of formatting edits actually. What happened? What happened there? I think it's just diff, which is a bit confused. Doesn't matter too much. Okay. So we have commit hard switch. Okay. So let's see. Are we done? I think we still need threshold. Yes, threshold. And then we're done with this series. I mean, not the whole series, but just as the implementation of the block-1 on ARM64. But we still have a lot of ground to cover. ARM64. So what am I trying to do? Threshold, yes. Focus. Activation. frame activation tests. So unit test, more unit test, and integration test. So relu, affine, leaky. Oh, and then we have soft sign. Oh, I have two more. Okay. So threshold looks pretty simple. So this one should work out of the box because it's going to be if x positive, we will need a load to put the 0 over there, but and we will need the sub. We need subtraction to because we cannot do if x bigger than alpha. We need to do x minus alpha positive. So that's a subconst. Okay, let's try it. So leaky, it comes after leaky. Yes, threshold. So it has an alpha, that's all good, and it's threshold relu, and so the function is if x bigger than alpha x, else 0. If x bigger than alpha, else x, else 0, which is ti 0. And then it should fail because it, let's have a look at the definition, but I'm pretty sure we implemented it with the sub. Leaky, threshold, yes, subconst. Okay, and we have the rest. So we'll do, we'll run the test. So it's threshold. And we'll do it's running. We'll right away do the unit test. So it's sub const alpha x minus alpha. It's sub I'm gonna break it and start again. I want to see it fail. So it's not this guy, it's subconst over there. And I think it will be as simple as yeah. Just need to be careful not to save, not to invalidate the test. I did save, but it's fine, it's installing, so add sub. Okay, failing with return non-zero, so unimplemented, so I just did it. Let's try it again, and we will do the test. Well, yeah, hopefully everything works, so let's go for it. So with this, we have done the 5 operation with consts. We haven't done the 5 ones. We need apps and maybe receipt for at least apps, I think, for soft sign and also reciprocate, which is good. And then, yes, it's just add and sub and min and max. Okay, everything is green, so I'm going to, yeah, we're going to do the last one. The last one is soft sign. Soft sign, so I guess now I can get rid of this. So in which order? It's between hard sigmoid and hard switch, so it's there. Soft sign. I don't think it has any parameters. And it's x over 1 plus absolute of x. So soft sign. And x over 1 plus x abs. Okay, it will fail. And if you look at the definition, it's using apps and it's using recip. So I chose to use a recip instead of using the division because not many, but not all. I mean, it's complicated. Some chips have reciprocate and do not have division, like the ARM 7 SIMD unit. It cannot do division straight away. So you have first to reciprocate the number below, and then you have to multiply it by the numerator and denominator. So we are going to write a unit test for apps. Starting to be a bit crowded over there, but where was apps in the order of the opcode frame activations? So apps comes right after load. So load, apps and recip actually, and before add, so they come here. So this one should be enough. So apps will be easy. Well, actually, the other should be fine too. So we're doing apps. And I'm going to do the other guy right away. So the funny thing is I'm not sure what it will happen with recip, because prop test will definitely go for zeros. So 1 over 0 is like the universe explode and everything. But I think that in float it will just return an infinite value, and so it should actually work. I think. I'm not sure. We'll see. And if it can't, then we will need to refine the strategy, at least for this guy, to avoid zeros in the test. But I think that it should work out of the box. Let's try if apps is working. No, this commit message was wrong. It was not our switch. It was, I don't know, leaky or something like that. Doesn't matter. Okay, so we are moving to the assembly, and we are going to do apps. And so we need to go back to our big documentation. And so where is apps? Is it fapps? It is fapps, tout simplement. Really easy. fapps, half precision, norm 82. Why is it? Yeah, single precision, double precision. That's what. What's the difference? Oh, this one takes just one value. Okay, vector. Hence the name scalar, or the mentioned scalar. So, and we need to source destination, or rather destination source. So we need to look at maybe we can start from there. Remove the last column. And change by fapps. Okay, let's test apps. Boom, 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 boom. Apps is working, and at this stage recip should be failing. Yes. And so let's just do recip. Back to this terrible documentation. I'm hoping it is frecip. Reciprocal estimate, okay. Reciprocal step and reciprocal exponent. All right, okay, so it's a mess. It's a bit of a mess. Let's see if we have another option. So what is this about? It's because so we have fdiv actually. So we'll use fdiv because it will be easier, I think. Yes, we'll use that one. So what is it about? What is this reciprocate step and stuff about? It's because that's the way it's actually implemented also on ARM7. So the idea is you have a first instruction. So it's same for square root actually. Where we frecip. Okay. So this instruction compute an estimate of the reciprocal, which I call reciprocate for like half an hour. And once you've done this, then you have this second instruction that refines the result. I mean, so it's kind of, I'm not sure it's Newton, but it's a numerical way to get to the reciprocal value. And so you need to do 2 or 3 steps in order to get to the right place. So I don't want to do that again. So I'm going to use fdiv, even if I won't have the choice on platform which doesn't have division. I will have to use reciprocal approximate and stuff. So with fdiv, what we need to do is we are going to need a 1 in one register. So can I use a load of 1? I think I can. I think there should be a fmove immediate. These instruction copy an immediate floating point constant into every element of the CMD. Okay, so that is a way to put ones in V24. So fmove in V24 for S, we're putting the value 1.0, and then we are doing, so I get rid of this, we're going to use this one as starting point, and so I'm going to store in A the result of F24 divided by A. So I can get rid of this, and here I just need to add v24.4s. Here we go. And it's not a mul, it's a div. If I do a mul by 0, it's not going to be super interesting. Mul div. Okay. Let's test recip. And if recip is working, if apps is working, then I guess recip is working, yes. Then I guess we are done with this because hard switch was already working. So let's try active. So now active will only test because there is a bit of inconsistency in the naming of both series of tests, but so we have everybody. We have if it were sorted, it would be better. We don't have ReLU actually. We haven't made a test for ReLU because ReLU is mask const with 0, but ReLU is working, and we have affine. Over there, we have leaky and threshold ReLU, leaky and threshold. We are missing threshold ReLU. Okay. So threshold, no, it's there. I missed it, but it should be there. Oh yes, it's all alone over there. Okay, so threshold we have. Hard sigmoid, soft sign, and hard switch. Hard sigmoid, hard switch, and soft sign. Soft sign is over there. Okay, so we have our block 1. I don't consider it completely finished because we still have a couple of unsupported. So these one are not used, but I think it would be better to have them right away. Should I do them right now? Yeah, why not? It shouldn't be too long. Yeah, it should be pretty straightforward. So first the test, new, first the commit actually, git diff. So here we have commit, we have threshold, and we have soft sign. So let's do the missing bits. So first the tests. So add sub mul max min mul. So I need 5 of them. Like these. And so add sub mul min and max. Add sub mul min and max. So who said assembly was difficult? Really? Add okay, so they're not working yet. It's fine. Mul by sub. Oops, what's wrong? S mul sub mul f mul by min and mul by max. And yes, there is potential to use. I mean, we have a scripting language over there, not a scripting language, but a templating language. So there is, a lot of possibilities to make it more compact and not having to write all of these, but at least we understand what we are doing. And that's it. We have our file operation defined. So if I look at it now, we are missing swap B and C. We are missing FMA and flow. And the where to the power of an int that we need to compute the exponentiation function. Tiny bit of formatting here, and I guess that with this I'm going just to commit all of that and maybe go and play a bit of Zelda, not on Twitch, because I'm not super skilled at video game, even if I like Zelda. And yep, or watch the Succession episode maybe. So that's missing ops, and with this, people, well, that's it for tonight. Next week maybe next week we should bench all of this, because we haven't done that for a long time, and I think benching would be nice to see to see how fast it goes, to compare it to the previous implementation, to naive implementations. So yeah, maybe next week we're coming back to the bench topic, and so see you all pretty soon.